What is going on, everybody? Today I'm going to talk about reinforced, cross-modal, and self-supervised imitation learning for visual language navigation. I'll be calling that VLN often. So to start off with, I just want to go over some vocabulary words. So VLN, and also some acronyms. VLN, which I stated earlier, is literally just visual or vision language navigation. It effectively means to use both sound to bring in a list of commands and then use our sight in order to complete and corroborate with those commands. In order to get to from one spot to another. Usually for ground-based vehicles, and in this instance for ground-based vehicles, but I am assuming this can be for UAVs or any other sort of intelligent embodied agent that's just trying to get somewhere, which we'll be using a lot in this PowerPoint as well, but it effectively just means it's a robot. For now, think embodied agent is a robot. Another acronym they use all the time is SIL, which is self-supervised imitation learning, which is effectively self-supervised learning, but it's basing it on prior experiences as opposed to having to explore the whole new experiences in order to get that again. So, there are three major problems regarding this VLN. It's the cross-modal grounding, which involves getting from point A to point B. The ill-posed feedback, which has to do with, getting the reward for getting the objective, but you have two robots. One takes the quickest path, one navigates the outside edge of the house all the way till it gets to its objective. If they were to both get the good job you made it, that would be ill-posed feedback. And I believe the generalization problem has to do with unseen environments. The robot needs to, okay, well, this is a house. I don't know this exact house, but I'm going to generalize. It needs to be able to react in unseen environments. So self-supervised imitation learning, it helps the agent make decisions about unknowns based off its prior experience, like I was saying with which helps us solve this generalization problem. RCM is the other novel approach that they talk about, which literally just adds reinforcement, that's the R, to cross-modal grounding method. So they're just taking the traditional point A to point B methods and they're adding a bit of reinforced learning to it. Both of these methods, they increase accuracy of the navigation in unseen environments as opposed to previous methods which don't even test in unseen environments because it would just bounce around like a foolish robot. So the article starts off by talking about how in-demand ground-based agents are about to become, and we can see it as well in our own society. With like spot minis have been being a thing in the past little bit. I know, I'm sure Amazon's chomping at the bit to replace as many people with ground-based robots as they can, both for factories, in-home stuff. EMS, I'm sure there's a whole slew of different, reasons why they would want embodied agents on the ground to be able to listen to their commands and then execute it. So an embodied agent, it needs to be able to understand the commands given and then reconcile that with what it sees around it. If it can do that, you have a very successful machine that can do what you tell it to do. We also need to define success more accurately, is what this paper is proposing. Like I mentioned previously, as in two people taking very different paths, one's very efficient, one's not, or two machines taking very different paths and getting the same reward. So in here, rewards are both created for listening to each subcommand, and also completing its ultimate objective. So I'm telling a robot, move towards the open door, then move towards the stairway, go up into the kitchen, find the open window, and stand next to it. That's a whole series of different things that it needs to understand, and then each time it makes it to the doorway, it gets a little reward. Little reward. So when we tell it to do these things in an unknown environment, it doesn't already know where this window is in relation to the stairs. It just has to do each thing and then figure out what's coming next. So these methods of these intrinsic reward systems, these little rewards along the way, really help in unseen environments. The related work they're building off has a lot to do with vision and language grounding separately, but there was a couple articles that talked about the importance of bringing these two fields together, because a lot of scientists think that much like humans, by, I use this word a lot, but reconciling the world around it, both visually and being able to identify individual things and put a language to it, it really will help the robot understand where it's at. Well, I mean, understand where it's at, but also help us lead them to a point where they could fully understand where they're at. All the prior work in combining these has been in static imagery, though. So the SC, static camera, static object, or the static camera, moving object. But with an actual moving agent, it's incredibly difficult because the room changes every couple of commands. The image, the everything changes. So an embodied agent, in order to be useful, it needs to be able to navigate in 3D environments. There's a lot of practice, and I see a lot of simulators that do like 2D top-down. Like a Roomba really effectively only operates in a 2D environment. It only considers the ground and the ground footprint, where we need things that recognize, up a stairs or there's a thing I can go over. Perhaps we give robots, more robots end up getting legs. It can go over something. It needs to be able to recognize what it can go over. The previous articles suggest various methods that this paper builds on. Most including this article, do a reward system from intrinsic or extrinsic, but I don't think any of them have put those together and weighted them like this article does. And it has a lot to do with these intrinsic and extrinsic rewards in the unseen environment. It has a lot to do with this exploration versus exploitation problem. You take a robot and you tell it to explore, and it's gonna go learn its environment, but it's not necessarily gonna do anything productive with that, right? Even like humans, we're in school, we're in the explore phase. We're not actually, even in a CBL, we're not really doing anything useful. We're using that task to gain ability that we will then go exploit that. So the robot needs to explore all this stuff and then exploit. But with this self-improved learning, it uses the prior experiences, all these previous houses, as the exploration phase. So it doesn't really need to explore the house first. It's a way to bypass that and move right to exploitation, just using many previous models as a basis for that. So this reinforced cross-modal mapping consists of two primary modules, right? We got the reasoning navigator that has to take this, move to the door, boop, separate that, then move up the stairs. It takes it all and it processes the words, and then it turns it into machine readable, move X direction, turn 90 degrees. It has to take what is the door, and then it takes what it thinks a door from its vision, and then it puts those together, and then it's like, oh, that's my objective, and then it builds this little command, and it builds a series of commands. So we can see down here, this H of T, that's it also remembers. It's the history context vector. So the embodied agent, in order to know that it successfully got to these different places, it needs to remember all of its commands that it's done so far, as well as what it has to do in the future. And that's what this matching critic is. That's the little rewards that it gets each time it gets, to that door. When it completes a small section of this H of T, it gets a little reward. And also, that helps it keep on track. Because if it wasn't keeping track, it might take a wrong turn, but it wouldn't know to self-correct. It would just keep going and going, and all of a sudden it's like, whoa, I'm not even near my objective, thus I fail. But if it were to be able to self-correct and find that mistake in the moment, because it didn't get that reward, it might be able to successfully get to its objective. So these folks, they used both intrinsic and the extrinsic reward in conjunction with each other, which radically increases its ability in unseen environments. So an extrinsic reward, as I mentioned before, it's a reward for completing an exterior objective. I'm assuming if a robot had like a, some sort of arm, and you're like, put that cup on that table, and it like does it. If it gets once it gets the cup out of the table, good job, you made it. Once it gets to the final destination, extrinsic reward. The outside environment is compatible with our objective, extrinsic reward. In previous examples, any robot that got close didn't get the reward, which they differ from, because if it got close to the kitchen, you still want it to get some sort of reward, just so it can build on future iterations, instead of labeling everything it did as wrong and teaching the machine learning algorithm to not do those things. If it got close, you still kind of want it to do that again, but maybe figure out where it went wrong using that intrinsic reward system. So that SIL, the entire purpose of this, this imitation learning is to assist in unseen environments. It just effectively, it uses a replay buffer, right? So it remembers every time it did a really, really good job at something, and it stores a list of them and the environment in which it was in. So when it's an unseen environment, it pretty much takes the environment using the camera, and I'm assuming the camera, or I'm sure you could add other, odometry sensors, and there's a whole bunch of ways to figure out where the robot is. But it compares that against which one is most close to its replay buffer of very good behaviors, and then it executes that one. To me, that feels like muscle memory, like more human or animalistic, organic machine, and an organic embodied agent's muscle memory. That's what that feels like to me, which is a very handy thing, because it allows us to, just like this, it allows us to, you've never driven this specific car before, but if you've driven a bunch of cars before, you can drive this car because of muscle memory. For the actual experiment, they trained this one embodied agent on a data set that included almost 7,200 R2R, which means room to room path data sets. So it's an entire, free data set on the internet that they've already taught some machines to explore. They've let machines explore, almost 7,200 rooms, and they took all that experience and turned it into one data set that you can just shove into this robot that's never technically explored anything, but once that happens, it does. Because one of the biggest keys I've seen, the key things they're trying to solve in this is to let the robot navigate an unseen, because pretty much every day a home changes, a construction site changes. It's each day, minute by minute sometimes, hour by hour sometimes, depending on what the task is, its environment is going to change. So it's always going to be in an unseen environment. So they always train it in seen environments, but once it's good, they want to always test it in an unseen environment to get them true metrics. And that's what they did for their experimentation here. They evaluated based on 5 primary metrics, okay? So they got the path length, and that they want to be as short as possible. So before, that robot that took the longest way just by hugging the left edge, we'll say, something simple, always hug the left edge, and then you'll get to your objective. That guy's gonna have a huge path length, where the one that just took the hallway is going to have a very short path length. So you want that to be lower. The navigation error, making it all the way into the kitchen, low navigation error. Making it a few feet from its actual objective, small navigation error. Completely different room, we want massive navigation error. We want that to be smaller. There's something called the Oracle success rate that has to do with letting it know if it got close, when to stop. So if it can't necessarily complete its objective, it's like I believe it acts as a, it got to a point close to its objective, so then it can shift towards different focuses. We measure the success rate, which we obviously want to be high out of all the different iterations, and then we also measure the success rate weighted by the path length. So again, us two successful robots, but one has a huge path length, we're going to measure that success. That's going to be weighted down a little bit. That's only going to be a fraction of. So once we get to the actual testing, we can see that it is incredibly more powerful than the previous methods. As far as the actual path length goes, you can see here it doesn't necessarily increase the path length, or it doesn't decrease the path length much compared to normal methods. But once we start looking at these success rates, and we start looking at how close it is to the objective, we can see that even in an unseen environment, it's way better, which none of these previous methods can even test against an unseen method, as, again, they would just bounce around because there's no function to these previous methods to navigate, which makes it hard to compare to a SATO state of the art. That's what SATO means. So compared to other state of the art methods, it's much better in unseen environments, and really can't compare to other state of the art methods when looking at unseen environments. So there's something called the speaker-follower method, which this builds on, that they discussed in their previous work. And this method excels in every way except for the path length, which isn't measurable because it's, I believe, effectively just following someone. So, the path length could be any given thing. You can see down here, they did their RCM model, and each of these, I believe, this is without the intrinsic reward. This is without the extrinsic reward, which makes it pure supervised learning. And cross-modal, this is without the cross-modal reasoning, which they implemented. And again, the RCM plus, when you combine their two novel approaches, even in an unseen environment, the numbers are incredibly low. Again, maybe not for path length, but for things like success rate and the Oracle success rate, they're much higher, which we want. And you can see here, we want path length to be low, we want navigation error to be low, but we want the success rates to be very high. Whoops. Using the scroll wheel. Arrow key, much better. So the paper didn't really mention anything about future work, but I would like to see more thought given to this reward system. So they were able to stack two reward systems on top of each other, the extrinsic and the intrinsic. I would like to see different types of intrinsic rewards, maybe for both following commands and, let's say, in the future, let's say getting there safely, getting there without disturbing the environment could be another internal reward. This idea of rewarding a machine based on how successfully it completes its objective and the different ways in which we define success, and then we can give it different rewards based on that. I would like to see, again, these layered with other objectives, like not only get there shortest, but get there without disturbing anything, get there as quietly as possible, perhaps getting from point A to point B, without not being noticed. But if I've got a home robot, I don't want it clunking and clanking and making a ruckus. You want it to be kind of discreet. You want it to be, so perhaps maybe we could reward it for taking the path that creates the least amount of noise or something like that, or gets in people's way the least. Perhaps you've got some machines, some embodied agents in a business, and there's a lot of foot traffic. Perhaps where there's a lot of foot traffic, these should avoid, because we don't want to get in people's way, customers, workers, whatever. In conclusion, this paper produces two novel approaches, the RCM and the SIL. That's the reinforced cross-modal learning and the self-supervised imitation learning. The tests demonstrate that it's effective for both the standard, traditional, here in the moment, room by room style learning, and for this lifelong, continuously changing environment setting. They were the writers of the article were mentioning that these methods are good for other applicable learning models as well. So I think what they mean by that is it can translate to like air-based embodied agents, water-based embodied agents, and perhaps not even embodied agents at all. Perhaps this means, what they mean by that is that by layering intrinsic and extrinsic rewards, we can make other reinforced learning procedures and functions operate better as well. And they were huge on this whole idea of a fine-grained intrinsic reward and a coarse extrinsic reward. And I really find this approach intriguing because it operates so much like organic, machines. Us, I mean. So we get to, you're looking for your class, right? You feel you're like, oh, I made it to school. Little reward. Your brain gives you a little reward. Oh, I'm looking for Molinaro 130. Oh, I'm in Molinaro. Whew. Little reward. I'm closer to my objective. I see 135, 134, little reward, little reward. Those are the intrinsic rewards. I am, following. I know I have to do these things in order to get there. So I'm by completing my little objectives that I know will lead to my final objective, I'm getting little rewards. And then once I get there, I get that massive reward. And I find that to be incredibly intriguing because it emulates what organic life does, and I feel like that could be applied to not only robotics but a bunch of different areas. And that is all I got. Thank you for watching. Catch you next time.